In this video, we will prove some results that we used in the previous video. So go and check out the previous one if you've not seen this one. But there's a lot of stuff written down, but let's go into it as simply as possible. So if we have a complex number z1 and it's equal to r1 times cos theta 1 plus I sine theta 1, where r1 is the modulus of z1 and theta 1 is the argument of z1, and then likewise for z2, then we have the following two sets of results. So first of all, the modulus of the product of z1 and z2 is the product of the moduluses of z1 and z2, and the argument of the product is the sum of the arguments. That's the first set of results that we're going to algebraically prove. Then we also have the modulus of the quotient of z1 and z2 is equal to the quotient of the moduluses of z1 and z2. And the argument of the quotient of z1 and z2 is the difference of the arguments. So a lot of stuff here. In the previous video, if there's a bit of information overload, in the previous video we did do an example where we used both of these results. So I think it's always good if you're trying to get your head around something to actually do an example first and then try and prove it. But as I said in the last video, I just want to make something very clear. The way that I'm going to do this in this video is not the conventional way of doing it, because the conventional way of proving these things is actually very simple. You use the exponential form of a complex number, and it's like one line of working out for each one. It's really simple. But I'm going to assume that you don't know about the exponential form. So if you do, then this is kind of just a fun exercise to try. And if you don't know about the exponential form of a complex number, if you're listening to me right now and you're like, what is that? Then it's okay, because we can do it without. So all you need to know about for this is basically just polar form, or modulus argument form, as some people call it. So let's just dive straight in. So the first thing we want to do, the first set of results, is the results that talk about the product of z1 and z2, okay? So let's actually take z1 and z2 and literally multiply them together and see what happens, okay? So let's do it right now. Exciting stuff. So z1 times z2 is just going to be r1 cos theta 1 plus I sine theta 1. Remember, that's what z1 is. And z2 is r2 cos theta 2 plus I sine theta 2. And basically all we're doing here is we're going to try and find the modulus of this new number, and we're going to try and find the argument of this new number and see what it is in terms of the modulus of z1, the modulus of z2, the argument of z1, the argument of z2. That's all we're trying to do. So continuing this line of working out, let's put the r1 and r2 next to each other here. So we've got r1 times r2, and then I'll do a big bracket, and then we can expand this all out. So we've got cos theta 1 times cos theta 2. That's the firsts. That's a theta 2. Let me rewrite that, make it super crystal clear. That's a theta 2 there. Outside, we've got cos theta 1 times I sine theta 2. So that's I times cos theta 1 times sine theta 2. And I've just realized that needs an extra bracket there. Okay, inside, we've got I sine theta 1 times cos theta 2. So that's plus I sine theta 1 cos theta 2. And then finally, last, we've got I sine theta 1 times I sine theta 2. The i's are going to times together to make minus 1. So we're going to end up with minus sine theta 1 times sine theta 2, just like that, okay? So already it looks like a lot of algebra, but we can simplify this quite a lot. So this is r1, r2 times, and then all we're going to try and do here is put this result into modulus argument form, into polar form itself. So we just need this to be basically cos something plus I sine something. That's what we're trying to do. So let's get all of the real parts of the inside of these brackets in one area. So we've got cos theta 1, cos theta 2. The only other term that doesn't have an I in front of it is this last term here. So we can say this is cos theta 1 times cos theta 2 minus sine theta 1 times sine theta 2. Then I'm going to do a plus I, and then in brackets, I'm going to do all of the stuff that has an I in front of it. So cos of theta 1 times sine of theta 2 plus sine of theta 1 times cos of theta 2. Just like that. And I think that's one more bracket needed. Okay, cool. So now, if you're an eagle-eyed viewer, you might notice something. You might notice that actually we can use the the compound angle or the addition formulae to simplify these, right? So cos theta 1 times cos theta 2 minus sine theta 1 times sine theta 2, this actually is the same thing as cos of theta 1 plus theta 2, because that is the compound angle formulae for cos of theta 1 plus theta 2, okay? And likewise, cos of theta 1 times sine of theta 2 plus sine of theta 1 times cos of theta 2, that's actually, again, the addition formulae or the compound angle formulae for sine of theta 1 plus theta 2, okay? And now what you can see here is we've now got our complex number, z1 times z2, in its own modulus argument form, right? Because it's in the form something times cos something plus I sine something. It is. So here we can see, well, the modulus of this new number z1 times z2, the modulus is r1 times r2, right? And the argument of this new number z1 times z2, what's the argument? Well, it's theta 1 plus theta 2, right? Because we're just comparing this and this and this. That's all that's going on. Now, what did we say that R1 and R2 were? Well, there, the moduluses, if we go back up, they are actually the moduluses or moduli of Z1 and Z2 respectively. So R1 is the modulus of Z1 and R2 is the modulus of Z2. So now we have this great result that says that the modulus of Z1 times Z2 is the modulus of Z1 times the modulus of Z2, which is what we set out to prove. And then here, the argument we can see, let's talk about that. The argument of z1 times z2, how can that simplify? Well, we've got theta 1 plus theta 2 here. Well, what is theta 1 and what is theta 2? Well, remember, guys, we've said it. Theta 1 is the argument of z1 and theta 2 is the argument of z2. So all we've got here is that the argument of z1 times z2 ends up being the argument of z1 plus the argument of z2, just like that. And now we have proven, if we go back up here, we have proven the top line. We've proven this, and we have proven this, okay? That's what we've just done. Now let's go and divide the complex numbers, and we're basically going to do the exact same thing. Okay, guys, so now we've got z1 divided by z2, and I've done a little bit of work here just to rewrite it in, again, in polar form or in modulus argument form. And now, again, we're trying to get this thing in polar form on its own. So we want to get this whole fraction in its own right into polar form. That means I want to be able to write this fraction as something times cos of something plus I sine of something. At the moment, it's not in that form. I want it to be in that form though. So first thing I'm going to do is I'm going to factor out the R1 over R2. So I've got R1 over R2, and then I'm going to do a big bracket, and now I've got cos theta 1 plus I sine theta 1 divided by cos theta 2 plus I sine theta 2. And you might say, well, how on earth are you going to get this into, you've got to stop it from being a fraction to begin with. So I'm going to do a very clever trick, guys. So I'm going to what you call realize the denominator. So that means that I want to make the denominator a real number. You might recall the way that we do this is we multiply the top and the bottom of a fraction by the complex conjugate of the denominator. So I'm going to times the top and bottom of the fraction by the number 1 in a fancy way. I'm timesing the top and the bottom by cos of theta 2 minus I sine of theta 2, because do you see that's the same thing as the denominator, but I'm doing the conjugate. That means that if there's a plus in x plus iy, I'm going to make it a minus, and if there's a minus, I'm going to make it a plus. I'm doing this because when I expand the denominator out, you will get the difference of two squares, which forces all of the complexness to become real. You'll see. So now if we expand out the numerator, we've got cos of theta 1 times cos of theta 2. Let's write that in. There we go. And then let's do outside. So cos of theta 1 with a minus. So minus I times cos of theta 1 times sine of theta 2. Inside we've got I again, so plus I. And we've got sine of theta 1 times cos theta 2 there. And then finally, we've got I sine theta 1 times minus I sine theta 2. So the I and the I become minus 1, but there's already a minus there, so it becomes plus. So we've just got plus sine theta 1 sine theta 2, just like that, okay? So that's the numerator. Okay, a very complicated looking numerator, but we will simplify it in a second. This is my awful fraction line. Ugh, it looks terrible. Then, guys, I'm not going to do all the working out here, but you can actually see if you expand this out, what you will end up getting is cos squared of theta 2 plus sine squared of theta 2, okay? If you don't believe me, you can try and expand it out, but take my word for it, you will get that if you expand out the denominator. And again, if you know anything about trigonometry, you know that cos squared theta plus sine squared theta is the number 1. That's the Pythagorean trig identity. So now we've successfully got rid of the fraction, right? Because this, we can just ignore it because we're dividing by the number 1, okay? Now, if we, once again, split the numerator, which is now just the whole thing, into the real parts and the imaginary parts. So the real parts is the stuff that don't have an I in front of it. So cos theta 1, cos theta 2, and this time it's a plus. So plus sine of theta 1 times sine of theta 2. And then let's do a, because we want it in modulus argument form, we want it in polar form. So it needs to be cos of something plus sine of something. So I do want there to be a plus there. I need plus I, and then I'm going to go, what am I going to write? Well, I'm going to go sine theta 1 cos theta 2 minus cos theta 1 sine theta 2, just like that. And I think I've just about got enough brackets there. Cool. And remember, the fraction's gone because we're dividing by the number 1 there. Okay, cool. Now, again, if you're an eagle-eyed viewer, you will notice again that we can use the compound angle formulae, or the addition formulae that some people call it. So what's this? Well, the first one is actually cos of theta 1 minus theta 2. Okay, so the compound angle formulae for cos of theta 1 minus theta 2 is this. So we can replace it, okay? And then same thing here. So we've got plus I, and then actually this thing here is the compound angle formulae for sine of theta 1 minus theta 2. So we've got I sine theta 1 minus theta 2 there. As you can see, this is now indeed in polar form, which is what we wanted. And guys, remember, this was Z1 divided by Z2. So now we can see that the modulus of Z1 over Z2 is just R1 over R2, which, remember, R1 is the modulus of Z1 and R2 is the modulus of Z2. So that's the third result out of 4. And then the argument of Z1 over Z2 is just theta 1 minus theta 2. And again, that's the argument of Z1 minus the argument of Z2. Okay, so now we've proven all 4 results. Okay, so just going back up so we can look at what we have finally done. We've now proven this result as well. And we've proven this result here. And again, guys, I just need to be super clear about this. Don't come at me in the comments and say, oh, actually, there's a simpler way. Yes, there is, but I'm assuming that we do not know about the exponential form. That's a new form of the complex numbers, okay? So we've got rectangular form or Cartesian form. We've also got polar, or some people call it modulus argument form. And there's also the exponential form. And if you know the exponential form, everything that I've done in this video, you can do it like that. But as an exercise, okay, and also for people that don't know it yet, this is how it works, okay? So if this is where you're up to in your knowledge of complex numbers, this is exactly what you need. So hopefully that was helpful, guys. I highly appreciate everyone watching the video and sticking around to the end. Please do subscribe if you found the video helpful. I've got lots of other videos on complex numbers and other topics. Thank you for watching, and I'll see you in the next one. Cheers.